Now we deal with electrical energy and power. Okay, so electrical energy and power, right? And power. So let's try to understand what happens here. Okay, okay. So let us say I have a conductor. Okay, a conductor like this with end A, with end A here and end B here. Obviously, let's say the cross section is a circular cross section. Okay, it is a circular cross section, and it is something like this. Correct. Now let us say that this end A is at a potential of VA, and this is at a potential VB. Okay, and let us say that VA is greater than VB. Okay, now it means that there is, if VA is greater than VB, then while coming from VB towards VA with a unit positive charge, you must be doing work, right? And that is possible only when, you have the electric field that is pointed like this, right? The electric field which is pointed like that. Okay, only then is it possible. So a uniform electric field exists. Okay, and I call it E. This field is E. Okay, now what happens, the electrons, they'll start moving to the left, correct? So an electron here under this field obviously does not move straight. We have seen it keeps on moving in random direction and then keeps on getting collided with so many electrons and then kind of travels. But the net effect is as if it is traveling to the left, from the right to the left, with a speed, with a velocity vd, which is called the drift velocity, right? This is what is happening. Now let us try to understand, let's try to track an electron which is at this end, and this is an electron. What is its potential energy? Its potential energy is EVB, correct? This is its potential energy. What is its kinetic energy? Its kinetic energy, what is the velocity at this end? We have seen that the drift velocity, the drift velocity is a constant. It does not change, right? So it is half m m vd square, is it not? Now let us come to this end. What happens at this end? When this electron moves all the way and reaches here, what is its potential energy? It is U2. Okay, let's call this U1, right? Let's call this U1 and K1. This is U2, this is U2, and that is equal to what? That is EVA, right? This is EVA. What is the kinetic energy here? That is still this half m vd square. Okay. Now let us talk about the total energy. Okay. What has happened? The total energy is the sum of these two. Okay. And this is negative. So don't forget that this is minus, and there is a minus there as well. Why? Because this charge is a negative one. The charge is a negative one. right? Now what happens? See, the kinetic energy remains the same, so there is no change there. The potential energy, here is what?
It is more. It is more. It is more than that.
Is it more or is it less?
But isn't VA greater than VB?
Hold on. VA is greater than VB. I multiply it by E, a positive number, inequality holds. I multiply it by a negative number. I multiply it by -1. EVA -1 EVB. Which becomes less, which becomes more?
VB becomes more.
The sign flips.
Yes.
So it becomes this. So I'm saying minus EVA is less than minus EVB. The potential energy went down. Had this not been colliding with so many electrons in between, what would I have expected? I would have expected this velocity to be higher. Correct? This velocity would have become higher. This is not becoming higher. So the potential energy is not getting converted into the kinetic energy. So what is happening in the way, okay, so the total energy at A is less than the total energy at B. Why? Because the KE remains the same and P has gone down.
But if it is colliding with other particles, उसकी energy कम नहीं होगी.
No, it's not. See, that is the whole paradox. It is colliding, but the collisions are elastic collisions. Okay? So the velocity is not reducing due to that. But due to collision, it acquires a steady velocity, constant velocity, even though the particles are getting accelerated.
Acceleration is there, but our VD is constant.
But VD is a constant. Okay? That's a paradox. Looks like a paradox. But it's not. Why? Because it keeps on colliding with others and eventually moves with a constant velocity. Okay? We have done that derivation where their initial velocities, they vanished. Right? Now what happens? If total energy at this point is less than this, where has the energy gone? How about the law of conservation of energy? What has happened to my energy? Okay? What has happened? That this energy, okay, this is less than that. So this amount of energy, an amount of energy, see the final minus initial, minus EVA minus EVB, it is equal to what? It is E minus EVA minus VB, and that is nothing but minus EV. Okay, this is the loss. Okay, it seems to have been lost. It seems it's not there, and if it's not accounted for, it'll straightaway violate the law of conservation of energy. But that does not happen. This loss appears as heat. So actually this loss,
it's getting lost with the negative side.
Loss, yeah. Final minus initial is negative. It means my final thing has gone down. This loss appears as the heat energy, right? As the heat energy. Correct? Okay. Okay. So what is that heat energy? How much is that heat energy? And in what time? Okay, in what time? In a time delta t, small t, right? In a time delta t. Now let us try to understand. It's not a difficult thing to do. If this length is L, then two things happen. Then you can tell me, you can tell me what is the time taken for this electron to move at a constant speed from the end B to end A. That we can tell. What will that be? So delta T is nothing but L divided by Vd. No? Distance upon speed is equal to time.
Why delta T? Why not T?
Delta T. Yeah, T. You can say that's the time difference. No, you started here at say T1 and you ended up here as T2. So T2 minus T1 is termed delta T, right? So delta T is that. There is another relationship that you should understand. If I have taken a unit positive charge here and this is a uniform field of E and I have moved a distance L, I have been doing a work of E into 1 because I had a unit positive charge. So this was the force I had to apply without accelerating, and I moved a distance L, and that is equal to V, that is the potential difference, right? So what am I saying? I'm saying that VA minus VB is equal to a quantity V, right? It may be say 10 volts. I say it is V, okay? So I use these two here. What happens? This much energy has been lost. This much energy appears as heat, okay? In how much time? Delta T time, right? So energy lost E is equal to minus E V. This is not electric field. I'll say this is not electric field. Okay, this is say heat. Yeah, this is say heat energy H. Okay, minus EV in delta T. So energy per unit time. What is that? So energy per unit time is what? It is minus E, and V was E into L, right? E into L.
This E is electric field.
This is electric field. Yeah, correct. Okay.
Yes.
Okay. And L upon delta T is what?
Mm,
VD.
Is VD. Okay. So L upon delta T is VD. So it is minus E into VD. V VD, right? This is VD, but I should not have converted, say, and E is equal to V by L, right? EL is equal to V, so I should not have converted this in the first place. I should have left it
Yeah,
as V, right? I should have left it as V, so that this 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 would have remained what it was. This is E into V upon delta T, correct? E upon V into delta T, and what is that?
yeah, and that will become I because we have charge upon times.
We know that I is equal to N E A V D, right? This is equal to that. This is your total current, right? So my delta T is what? I had my VD is equal to L upon delta T, is L upon delta T, L L upon delta
Charge upon
T.
time is going to become
Yeah,
You can just do charge upon time.
Charge upon time is correct, because maybe in delta t time you have one electron that is gone, right? You can also do this, because this will also kind of lead you to the same result, right? Say in time delta t, you can say, because it's not that in 1 second only one electron, in delta t second only one electron is gone. How many electrons would have gone from here to here? How many electrons would have gone from here to here in time delta t? The same thing, okay? N E A V D delta t is equal to I delta t. That is the amount of charge that is gone. Okay, so that's why it's not proper to kind of write that in delta t time, though it's not going to change anything, right? It still give you the result. Okay, so I know that in time delta t, so much amount of delta t into so much into delta t, so much amount of charge is gone, right? So what is that equal to? E upon delta t, E upon delta t, or you can write this as, this is your V. E upon delta t is nothing but E upon delta t is nothing but. Now what happens in this time delta t? In this time delta t, how many electrons will pass through this? How many electrons will pass through this? Yes. How many electrons will lose their energy by so much?
And
The current.
In that time, the all the electrons that were in time delta t, all the electrons that were a distance vd delta t behind, everything will pass, correct? Those who were here in delta t time, it will travel vd delta t. So everything within the vd delta t would have traveled.
And like on volume to volume.
Okay, so what happens, this is for one electron, right? Now in time delta t, how many electrons go?
Number
We have everything within vd delta t going there. So there's a slight mistake here. Okay, what happens, the number of electrons that go are vd delta t into the cross sectional area, that is the whole volume. So everything contained within vd delta t multiplied by a volume, and that multiplied by n is the total number of electrons, and each of them is carrying a charge of so much, and then it is, so there are so many electrons, okay, so many electrons, which are so many, this is the total number of electrons. Let's not lose sight of that. This is the total number of electrons, and each electron is losing an energy of EVA, minus sign I have put here. So not EVA, it is EV, right? This is the loss by each electron. So in time delta t, the energy that appears is so much. So if I divide it by delta t, okay, this delta t comes in here. So I am left with this is equal to n e a v d, okay, in n e a v d into v, right? And what is n e a v d? N e a v d is nothing but NeAVD is nothing but I. So this is the total heat energy per unit time. And if I take the mod of it, right? So this is the power. Okay. So this is the power. So power dissipated is VI. So power dissipated is equal to VI. This we have done already. We have been using this. But this is the proof of it. And we know that by Ohm's law, we know that V is equal to IR. So there is an, if I replace V by IR, then it becomes I square R. And I know that I is equal to V by R, so it can also be written as V square upon R. Okay? And that's that.
So won't we take n as number of electrons per unit volume?
Yeah?
Normally the equation में number of electrons की जगह number of electrons per unit volume लेते हैं.
Yeah.
पर हमने यहाँ पे ऐसे नहीं किया.
No, but number of electrons are infinite, you know. You have a 2-meter long cable, how will you go on calculating? But it does not affect you. It is the number density which is affecting this thing. Okay? We have seen that.
Number of electrons per unit volume is the number density.
Yeah, that is n, small n.
तो यहाँ पे वो n by
No, n is that, yeah. Here the small n is nothing but number of electrons per unit volume. Yeah.
that is why when we multiply the volume.
Volume, it became the number, yeah. It's not the total number. Right? So power dissipated is that, right? So these are three relations which are very, very important, and we keep on using them interchangeably as we go ahead, right? Fine.